To find inverse of a matrix, we learned how to find inverse using cofactors and also using row operations. Now, the next thing after this is some properties of inverse. Actually, I have written that. Yeah, here using row operations. Okay. Next thing is solving a linear system by using inverse. So, and this is something I told you before in the beginning, that a linear system can be written like this: Ax equal to B, where A is the coefficient matrix, X is the column vector, B is the right sign constant column vector. When use black color, when M is equal to N, we can find when N is equal to M, yani it is a square matrix. It is a square matrix. When it is a square matrix, we can find its inverse. If it is not a square matrix, then inverse is not defined for non-square matrices. So only for a square matrix. When N is equal to M and A is, when N is equal to M and A is non-singular, then we can multiply, we can solve this system Ax is equal to B by multiplying with A inverse from the left-hand side to this equation. We have Ax equal to B. To this equation, we multiply by A inverse from the left-hand side. Then, you know, the matrix multiplication is not commutative. Yani A multiply B is not equal to B multiply A in general. So that's why I'm saying here this word from the left hand side. So then A and A inverse will give you I. So I time X is equal to A inverse B, and I time X is equal to X. And what we are left with to compute A inverse times column vector B. So this is also a way to solve linear system. We have some questions in exercise, some examples which are already done in your book. You can look those examples and solve some questions. I will solve some question for you. Okay. Let us make here a note. When A is non-singular. In other words, when a determinant is not equal to 0. This means a determinant not equal to 0 mean A is non-singular. When A is non-singular. What does this mean? Determinant of A is not equal to 0. Then this system AX equal to B has a unique solution. We have seen before that sometimes a system has one solution or infinitely many solutions. Now, when A is a non-singular and it is a square matrix, when we say non-singular, automatically or by default, it is a square matrix, because for a non-square matrix, there is no inverse or singular or non-singular thing. So when we say A is a non-singular, so it means we are talking about its inverse, exist, determinant not 0. So then the system has a unique solution, not infinitely many solutions. Also, if there are two solutions, then that will give us some kind of a contradiction if we have two solutions, and you can verify this. Now, for a homogeneous system, I said this, mentioned this sometime before, I don't know, in class or to some student, that if we have a homogeneous system and A is singular, then the only solution exists is trivial solution. Now, the next thing we are talking about is homogeneous system and the result for this homogeneous system is that a homogeneous system of n linear equations in n variables, yani A is a square matrix. Ax equal to 0 has only trivial solution if and only if A is non-singular. So if A is a non-singular, then we can find A inverse, and when we multiply A inverse with Ax equal to A inverse with 0, this implies x is equal to 0. So the only solution we have is a trivial solution. So the next theorem is for homogeneous system non-trivial solution, that is when A is a singular. So a homogeneous system, let me also copy and paste this one here. You can see this non-trivial solution. A homogeneous system of n linear equations in n variable has non-trivial solution if and only if A is a singular. Non-singular, trivial solution. Singular, non-trivial solution. Singular, non-trivial solution. And non-singular, trivial solution. With this, we are done with these definitions and basic results. In exercise, first two questions are verified that these two matrices are inverse of each other. Simple, you can do that. Next question, use theorem 8.6.3 to determine whether a given matrix is singular or non-singular. If non-singular, then use theorem 8.6.2 to find inverse. Now this is question 3 up to 14. So theorem 8.6.2 and 3 they are using. What is this theorem 8.6.2? Finding inverse by determinant and cofactors. By finding determinant and cofactors. So here question itself is asking us how to solve it. And we did this question here. One example. By the way, this matrix of cofactors and then its inverse, this matrix is called ADJ. We read it as adjoint of A. Adjoint of A is equal to transpose of matrix of cofactors. Adjoint of A is equal to transpose of the matrix of cofactors. That is called adjoint of A. Somewhere you may see this word written adjoint of A. So you should know that adjoint of A means matrix of cofactors and take its transpose. Yani transpose of the matrix of cofactors is called adjoint of A. And then we found inverse. Although I didn't do this completely, here you can see example A equal to this matrix, and I show you how to find cofactors and ask you to complete this. And determinant, I did this here. So I showed you how to do these questions, number 3 up to 14. You do some of them for your practice. There are so many calculations involved in solving these questions, so it is necessary that you should do some good practice. Next question 15 up to 26. These questions are to find inverse using the row operations. I also show you how to find inverse using row operations. You can do this. Next questions, number 27 and 28 are to find the inverse of a product. For question number 27 and 28, use this property. If you want to find A, B, A times B inverse, you need to find B inverse, A inverse separately, and then multiply B inverse with A inverse in the reverse order. And B inverse, A inverse are given in these questions, so you simply need to multiply them. So if I show you this, let me do the easy one. 1 over 2 minus 5 over 2 minus 1 over 2 and 3 over 2. This is A inverse already given. And then B inverse is also given 2 over 3, 4 over 3 minus 1 over 3 and 2 over 3, 4 over 3 minus 1 over 3 and 5 over 2. So we want to compute AB inverse. We have to compute B inverse, A inverse, and that is, first I put here B inverse, 2 over 3, 4 over 3, negative 1 over 3, 5 over 2. I don't know it is correct or not that we have here 5 over 2. Maybe it is correct, because all other are over 3. Anyway, 1 over 2 minus 5 over 2 minus 1 over 2, 3 over 2. Now we multiply. How to multiply? We take first column and write here. Let me use, take first column of the second matrix, right here, 1 over 2 minus 1 over 2, multiply them and add. You know how to multiply. So 2 over 3 multiply 1 over 2 is 1 over 3. Minus 1 over 2 multiply 4 over 3 is minus 2 over 3. And we need to add them. So minus 2 over 3. Similarly, 1 over 2 multiply minus 1 over 3 is minus 1 over 6, minus 5 over 4. Now we remove this 1 over 2 minus 1 over 2 and then put here second column minus 5 over 2. Again, let me put this in blue color, minus 5 over 2 and 3 over 2. Now multiply them. So 2 to cancel, minus 5 over 3 plus 3 cancel, 2 4 cancel, plus 2 also. And then multiply 5 over 2 and 1 over 3. So it will be 5 over 6 and plus 3 over 2, 5 over 2, 15 over 4. Oh, I didn't change the color. Okay, anyway. And now you can simplify them. 2 over 3 1 over 3 minus 2 over 3 is minus 1 over 3. And here we will have 12 as a common denominator. So minus 2 and 3, 15 minus 17 over 12. And then minus 6 minus 5, 1 over 3. And here 12 is common denominator. And then 10 here and 15 times 3, 45. So it is 55 over 12. So this is the answer for question number 27. Let me check if it is correct. No, it is not correct. So I think it is 5 over 3. It is a writing mistake for this question number 27. It is a writing mistake in the book. It is 5 over 3. So we need to redo this because all other values are over 3, so it is over 2. So this make me suspicious. Anyway, let's do this. Now here I copy 1 over 2 and minus 1 over 2. Multiply this 2 over 3 and 1 over 2, so 1 over 3. And minus 2 over 3. And this will give us minus 1 over 3. And here the lower this row and this lower one is minus 1 over 6 minus 5 over 6. Now it is correct. Then we delete this and write here minus 5 over 2 and 3 over 2. Now multiply 5 over 2, 2 over 3, so it is negative 5 over 3 plus 2. And the lower one will be minus 5 over 6 plus 3 cancel. And then we have 5 over 2 left here. Okay. This is minus 1 over 3. This is plus 1 over 3. Minus 1 over 6 minus 5 over 6 is minus 1. And here, when we take this Tawheed Muqam, that is equal to 6. So minus 5 plus
5
15.
over 6, not minus.
Not minus?
Yes, teacher.
You are absolutely right. Minus minus plus. So you see, there is always a big chance of doing some plus minus mistake. And this is what I say sometime when that practice is very, very important. So it is 20 over 6, which is 10 over 3. So this was a trivial, easy question. Just for the sake of completeness, I did this one. Find if A inverse is given, then how can you find A? A inverse is equal to A. So if A inverse is given, you can find inverse of A inverse, and that will be the original matrix A. Okay. Then there are some other questions with some other properties. They are very easy to verify. Question number 31 is like this. That A is equal to 4 minus 3x and minus 4. Find x such that A is the same as A inverse. Yani A is its own inverse. Okay. For a 2 by 2 matrix, yani you have already seen this, that if it is A, B, C, D, 2 by 2 matrix, then A inverse is obtained as 1 over determinant of A, and then the matrix of cofactor transpose, we can write it directly. On the main diagonal, replace and interchange these two numbers on the main diagonal, and on the other diagonal, you simply change their ishara. This is direct method to find the transpose, the inverse of a 2 by 2 matrix. So one thing we note here, that in this matrix A is that we have a 4 and negative 4 on the main diagonal. When we interchange that, the first number will become negative 4 and the other will be plus 4. So one thing is to need to multiply by a negative. So, and also there is no quotient, nothing in the denominator. So this tells us that A determinant should be equal to negative 1. Why? Let me do this for this matrix A. So A inverse for this matrix is equal to 1 over A determinant, and then apply this thing same here. So you get minus 4 and 4 here. So, and what do you get here? Interchange them.
Minus x.
You get here minus x and get here
And 3.
plus 3.
Doctor, it's
Yes.
not.
The
We don't change the other diagonal. We just change the signs.
Oh, my mistake. Stupid mistake. Come on, man. 3 and minus x. We change only main diagonal. You are right. So now, to make this matrix as matrix A, we need to multiply by a negative. And also there is nothing in the denominator. So this thing tells us that A, so you can say this, is equal to A if determinant of A is equal to negative 1. Otherwise, it cannot be. So when determinant of A is a negative 1, then this matrix will become matrix A. Okay, this is one thing. And second thing is you need to find X. So of course, what is determinant of this matrix? Negative 16 plus 3x. And we put this equal to negative 1. So 3x is equal to 15. X is equal to 5. So when we look at the signs ishara of the elements inside, we see that there should be a negative outside, and also there is no quotient. So outside should be negative 1, not negative 1 over 2 or 1 over 3 or so on. So from here we see that a determinant should be negative 1. So we put a determinant equal to negative 1. And when we do that, we find the value of x, which is equal to 5. So this is what we need to do here in this question.
Doctor, why did you choose -1 to be the determinant?
Because you look at the main diagonal on this, let me put red. So look at this one. This is A inverse. This can be equal to matrix A if you multiply this by negative 1. Mazboot?
Okay, got it. Thank you.
So determinant of A should be negative 1. And we use this information that determinant of A is a negative 1 to get the value of x. Okay. Similarly, there are some other very simple, easy questions. Okay. There is one, say, definition or one thing you need to know and remember, that A is said to be orthogonal. If A inverse is equal to A transpose. Yani if A inverse is equal to A transpose, we call this matrix, or it is defined as, or people call this matrix, orthogonal matrix. If A inverse is equal to A transpose. So you find A inverse and then take its transpose transpose of the matrix A, you will see that they are same. Then part B of question number 33 is to verify that a given matrix is an orthogonal matrix. You can do that. And if A is orthogonal, then determinant of A will be plus minus 1. That is question number 24. Now there are some questions about solving the linear system using matrices. Nothing new need to be done to solve linear system using matrices. You simply need to find A inverse and then multiply the right hand side column by A inverse. That will be the solution. Let me do one question for the sake of completeness. Question number, let me say, which one? 49. Let me copy that question from the exercise to save my writing time. This is question number 49. So the solution. Okay, Shiva, we don't need to listen your music. Mute your mic. That is good. Now here we can write this system as AX equal to B, where matrix of the coefficients of this linear system is A. 1, 2, 2. 1, -2, 2. 3, -1, and 5. And the right hand side vector is 1, -3, and 7. Now we apply row operations on matrix A to get its inverse. For that, we need to write this augmented matrix 1, 2, 2, 1, 0, 0, 1, -2, 2, 0, 1, 0, 3, -1, 5, 0, 0, 1. Should I do this question? It is same like here.
We did yesterday or someone.
Yeah, we did this one example here. So exactly the same way you find A inverse. Find A inverse and compute x1, x2, x3 equal to A inverse multiply B. So that is obvious thing. Nothing more information you will get except just some this calculations and finding A inverse. So you can do this. Let me save time and do something, some other thing. In problem 51 and 52, write the system AX equal to B as X equal to A inverse B to solve the system for each matrix B. So this is a one system with the 3 right-hand side matrices. You can do that. In problem 53 up to 56, if you open your book on your screen, you can see that. Without solving, determine whether the given homogeneous system of equations has only trivial solution. Has only trivial solution or non-trivial solution. Without solving mean
We find the determinant.
you find the determinant. If determinant is equal to 0, it is a singular, so there is a non-trivial solution. Determinant not equal to 0, it is a non-singular, so there is only a trivial solution. That is only you need to verify. Okay, just for the sake of completeness, let me do maybe one of these questions, 53. So, okay, again, instead of say typing, let me simply copy it from here. Okay, so the determinant of the coefficient matrix 1, 2, -1, 4, -1, 1, 5, 1, -2 is equal to 1 bracket 2 minus 1 minus 2 bracket minus 8 minus 5 minus 1 bracket 4 plus 5. So this is equal to 1 plus 8 plus 5, 13 times 2, 26 minus 5 plus 4, 9. It is not equal to 0. So the system has only what? You tell me.
Only traveler solution.
A trivial solution. That's it. This is what we need to do in these questions. Okay, we are done with this section. There are many more questions. You need to solve them to make things more clear and have a good, very good practice. Now, the next section we have in our course is 8.8. 8.8, section 8.8, and the section 8.8 is the eigenvalue problem. 8.8, the eigenvalue have you seen before to find eigenvalues? How to find eigenvalues? Somewhere in some course?
Yes, in
Yeah,
202.
Math 202.
202. But there it is, I think, just for 2 by 2 matrices.
Yes.
Yes.
But I think we didn't study it carefully because the final.
Yeah, final is near, and teacher they just run fast for this section. So here we will study that in detail. Let me just copy and paste from your book this theorem statement. Let A be n by n matrix. A real number lambda, not real number, sorry, a number lambda, it may be complex. A number lambda is said to be eigenvalue of A if there exists a non-zero vector, solution vector K of the linear system. The solution vector K is called eigenvector corresponding to the eigenvalue lambda. So this is the definition. The word eigenvalue is a combination of German and English terms adapted from the German words eigenword. We translate as literally as proper value. So this is something history about this one. So now the next thing is how to solve this one, how to find the eigenvalues. So how to find the eigenvalues and corresponding eigenvectors. For that, we write AK minus lambda K equal 0. And then we write it as A minus lambda K equal 0, K common factor. But this is not true. We cannot do this because A is a matrix, lambda is a number. So we need to make this lambda as a matrix And for that, when we take something mushtarik in case of matrices, then what left at that place is not number 1, is the matrix I. Matrix I, identity. So AK minus lambda K, when we take K mushtarik common factor on the right hand side, because in matrices, this commutative property is not satisfied. So we need to be careful that we are taking a common factor from the left or from the right. Now this is a homogeneous system. You know, this right hand side is not a number, it is a column matrix. Homogeneous system. Now this homogeneous system has a non-trivial solution. This homogeneous system has a non-trivial solution. A non-trivial, you know, it is written here. Let me put underline in red color. If there exists a non-zero solution vector k, yani k is a non-zero, yani non-trivial. So this homogeneous system has a non-trivial solution, yani non-zero k. If a minus lambda I is singular, yani determinant is equal to zero number. Determinant is equal to zero number. How can we distinguish between zero number and zero vector? So let me make it like this. Long.
We can make bar under the zero.
We can make bar under the zero. You can do this, okay? So this mean column vector of zeros. Yeah. So this homogeneous system has a non-trivial solution if this determinant is zero, yani A minus lambda I matrix is singular. So we will solve this equation and then find the eigenvalues. Once we find eigenvalues, we will put back in this homogeneous system and solve the system. Okay, let us do this for a given example. Let me also example solution is given. Maybe should we do this for exercise or this example? Okay, anyway, we need to understand. So exercise or this example problem, that should not make a difference because we are just trying to understand.
Doctor.
Yeah.
Homogeneous is always singular and always has a non-trivial solution, right?
No. A homogeneous system has a non-trivial solution like let me write it. Ax equal to 0. This is homogeneous system. This has a trivial solution if A is non-singular. It has non-trivial solution if A is a singular. A singular, non-trivial solution. Okay.
Okay, singular non-trivial, non-singular trivial.
Yes, you write it. Actually, it is written here in the previous section 8.6. You see here is these two theorems: trivial solution, non-trivial solution. Okay.
Okay, thank you.
Now, let us do this example. This is example number 2 in your book. So, what is this determinant of A minus lambda I? Is this determinant A 1 minus lambda 2 1, 6 negative 1 minus lambda 0, negative 1 negative 2 minus 1 minus lambda. Is this clear to everyone, or you don't know how I got this?
Clear.
If it is not clear to anyone, he should ask me. No one is asking. So, okay. Let us expand this. We can expand this from any row, from any column. Okay. Now, second column, second row has a 0. So let us expand by second row. 6, then minus 1 power, number of row 2, number of column 1, then determinant of a 2 by 2, which is obtained by deleting the column where 6 is and the row where 6 is. So what left? You tell me so that I make sure you are getting this.
2 1 minus
1.
Then
minus 2, minus 1, minus 1.
exactly. Then minus bracket 1 plus lambda, then minus 1 power, this is second row, second column, 2 plus 2, and then the determinant. Now we are using this entry. So delete this row, delete the column. So what left is 1 minus lambda, 1 minus 1 minus 1 minus lambda. Okay, this is negative 6 bracket minus 2 lambda minus plus 2. Here is a minus of 1 plus lambda, minus 1 power 4 is 1, and then inside bracket is 1 minus lambda multiply minus 1 minus lambda and minus plus 1 here. So here from the first part, minus 2 and plus 2 cancel, and we have 12 lambda minus bracket 1 plus lambda, and inside let me put square bracket to make it look different from the other bracket. So square bracket here. Now it is minus 1 minus lambda plus lambda plus lambda square plus 1. 12 lambda minus into 1 plus lambda bracket. This and this cancel. Oh, 1 and minus 1 also cancel. So lambda square. This is equal to 12 lambda minus lambda square minus lambda cube. 12 lambda minus lambda square minus lambda cube. I can take minus lambda mushtarik, then I write here lambda square plus lambda minus 12, which is negative lambda, and lambda plus 4 and lambda minus 3. So this is a minus lambda I after simplification. So a minus lambda I determinant is 0 if lambda is 0 or 3 or negative 4. So these are the three eigenvalues. These are three eigenvalues. Now we need to find eigenvectors. So first eigenvalue, lambda equal to 0. Now with lambda equal to 0, we need to solve a minus 0 I k equal 0 vector. Okay, a minus 0 I. So it means by chance here eigenvalue is 0. So it means we need to solve a k equal 0 vector. Okay, now you can solve this maybe by using augmented matrix. So what will be the augmented matrix for a k equal 0? You can solve either by substitution, by using augmented matrix row operations, whatever method you like, you can use. Now, what are the entries of a 1 to 1? 1 to 1. Then 6 minus 1, 0. Then minus 1, minus 2, and minus 1. Now let us apply row operation, and that row operation is negative 6 times row 1, add in row 2, row 1 simply add in row 3. One, 2, 1, and right side is 0. Minus 6 plus 6, 0. 2 multiply minus 6, minus 12, minus 1, minus 13. Minus 6 multiply 1 is minus 6 plus 0 is minus 6. And right side will be no change because there are zeros. 1 minus 0, 0, 0. Okay. So one row is 0. And it should be 0. There should be one row 0 because determinant is 0. Not all non-zero. So from here we get negative 13 k2 small k2 minus 6 k3 equal to 0. So k2 is equal to negative 6 over 13 k3. K2 is negative 6 over 13 k3. If you like, you can reduce this into reduced echelon form, or you can make, if you want to make one more step, you can divide second row by negative 13. That is your choice. But still, you will get this same answer, k2 equal to negative 6 over 13 k3. So this is k2. What is the first row? K1 plus 2 k2 plus K3 equal 0. So K1 is equal to negative 2K2, yani negative 2K2 negative K3. Negative 2 multiply K2. It will be 2 and 2. Negative and negative positive, 6 to 12, 12 over 13. K3 minus K3. So if we take Tawheed Muqam, this is 12 minus 13, negative 1 over 13 K3. So now you look what here is underlined. So the vector K, and I'm saying here big K1, first eigenvector K1. Now K2 is in terms of K3. K1 is in terms of K3. Both are in terms of K3. Now choose a value of K3 for any value for K3. Choose a value for K3.
Minus 13.
Minus 13, plus 13. Now here you are free to choose any number for K3. Now we try to be nice so that we do not have quotient. We try to avoid quotient. So that is why you said negative 13. If K3 is a negative 13, what is K2?
6.
6.
K1, 1. Now, we can also have let's say K3, we say 26. Then what is K2? Negative 12. What is K1? Negative 2. Are these two different vectors? Are they linearly independent?
No.
Here we say the vectors are different if they are linearly independent. So my question is, are they linearly independent?
Dependent, Victor, because we can multiply one and get another.
Yes, so they are linearly dependent. If two vectors are linearly dependent, we don't consider them different. So I will write this as a note. Eigenvectors are same up to a constant multiple. You multiply by a constant, then you will not get a new eigenvector. That is the same eigenvector. Now, the second one, we take lambda equal to 3. Then a minus 3 lambda, sorry, 3 is for lambda, a minus 3I. This I should put in black color. So then,
Doctor,
yep.
I think the time is up. It's 10,
Oh,
24.
my mistake.
Yeah.
It is time. So you have seen the method. Okay. Try to do these questions at home, and we will continue next week from here. You should prepare for the first quiz. I put an announcement on Blackboard. You must prepare for the quiz 8.2, 8.3, and 7.6. So it's time now. You can leave. You are free to leave. You can leave. If you have any question, I'm here to answer your question.
Okay, thank you, Doctor.
Okay. Yes. Thank you.
I have a question.
Yes, Haitam.
Why did you choose any number for K? I can choose any number.
You can choose any number. That will give you the same eigenvector up to a constant multiple. And the eigenvectors up to constant multiple are same. they will not give you a different solution, different answer. Why? If you see this.
But how
Okay.
can I know if I'm free to choose any number or not?
You can choose any number.
In any question, I mean.
You know, before this. That is why we learned the solving linear system before this. You know, after applying row operations, we get a matrix in which, you know, okay, are you seeing this red color big line?
Yes.
I convert this linear system into equations. So I get what? K1 plus 2, K2 plus K3 equal 0. And negative 30 times K2 minus 6 times K3 equals 0. So this is what left after row operations. How many variables? Three.
In this 3. Yes.
How many equations?
2 equations.
2 equations. So if there are 3 variables and 2 equations, number of variable is more, number of equations is less, then there are how many?
So is
one free parameter, yani one free variable. Mazboot?
yes, yes.
So same idea is here.
Okay. Thank
Clear?
you. Yes, clear. Thank you.
Very good. Very good. Yeah, Shabab, like him. Anything not clear at any step,
Doctor,
ask me. Yes.
for exercise 27 in section 8.6, in matrix B inverse, how you know the last enter are not the same in the book?
Yeah,
How it's
because
not correct?
other numbers are 2/3, 4/3, 1/3. All are over 3 over 3 over 3. So that make me think that maybe it is a mistake. It should be 5/3, not 5/2. And when I check my answer in the book answer, that my answer was different than the book answer. So that make me believe, before I was thinking, then I believe that no, here is a mistake. So you also correct this in your book that it is not 5/2, it is 5/3.
Okay, thank you.
All right. Okay, guys, have a good weekend. Stay home, stay safe. See you on Sunday with good health, inshallah.
Inshallah.
Thank you, Doctor.